Okay, thank you much, everyone. Good afternoon. Trying to. I'm trying to allow the sharing of my screen, but it's not giving me that opportunity, which it oddly did just before. Do you have to relinquish to be able to?
I have stopped sharing my screen, so it should just work if you press share.
Yeah, that's exactly what I did before. Oh, hang on. Here we go. Screen 2. Allow. Are we getting there?
Yeah, it's about to show, I think. Yeah, we're good.
Okay, great. I was going to talk about some work that we did a bit earlier in the climate resilience program on methods to improve our ability to estimate the severity and frequency and duration of heatwave events, both past and the future. And when I talk about heatwave events, I'm actually talking about the actual events. So, you know, as the days get hot, the series of days, and then as they end. And to sort of illustrate the challenge, I was going to use the Moscow 2010 heatwave. Here we have 50 years of daily temperature data from Moscow, data above the 94th percentile. And the 2010 heatwave is represented here by these two little blue lines. And as you can see, there was 2 periods of hot weather. These are the hottest temperatures ever observed in Moscow, but they were also not only the hottest, but they were the hottest in terms of an extended event, the number of days that were hot. And so the challenge is, how do we calculate the probabilities of such events? Not just the actual magnitude of the temperatures, but the likelihood of getting these series of hot days. But the problem is that different events and different thresholds used, different durations, they all have different probabilities. And once you start to subdivide by duration or maybe time of year, you very rapidly run out of data and not be able to determine any sort of meaningful probabilities. And if you then want to look at the changes in such probabilities, then you've really got no hope at all, because you just haven't got any information. So an alternative that we're taking here is to try and build a statistical model that captures all the right characteristics and then simulate large event sets from which these probabilities can then be determined. As you can see, the probability of hot days in this particular graph changes very significantly with day of year, or DOY, but also within there's also a climate change signal, and obviously that will get worse as if we start to look into the future. So to correctly characterize sort of conditional probabilities, that is, given a hot day, what's the likelihood of another hot day, we need to remove this non-stationarity out, and then once that's gone, we can then characterize that conditional probability. So here's like a schematic of the sort of methodology or the approach that I've taken. If you start at the top left, we have a set of observed daily temperatures with day of year and climate change within them. We need to transform these onto a stationary unit scale, which I'll show how that's done in a moment. But one can think of that as converting everything into a probability. So wherever it lands, can you give it a probability? And then once you've done that, you can use it in a more flexible way. And actually, this work tends to be done on what we call the Laplace scale. Once we have all the data on a sort of common, uniform, stationary scale, we can then build this statistical model, which will take account of day of year and climate change that might affect the conditional probabilities. And once we have that model, we can simulate this large set by specifying a period of the year, a range of days of year, or a year for a particular value of climate change, and get a large set of simulated data, which we then back transform onto the observed scale, reintroducing this non-stationarity, from which we can then calculate our heatwave metric of choice. So to make stationary data, to show that it is possible, here is some example data from a GCM force with the SRSA2 scenario. And you can see those as the black dots, and against year on the left-hand side and day of year on the right-hand side. And the red line is this derived non-stationary climatology. You can see from the left that it increases by year, but also on the right how it varies through the year. And actually on the right-hand side, the bottom line corresponds to the year 2000. The solid central line is 2050, and the top dash line is 2100. So you can see how it evolves as we go through the century. And if you subtract this red line, you get this the black dots on the left. And you can see that most of the climate change has been removed, but there is a little bit, there's a degree of increasing variance as we go through the year. So we remove this with a further sort of location scale transform dependent on year, which then gives the green points, which are down here. And so you can see that with year, this is nice and stationary, but also on the right-hand side, the green points are now plotted against day of year, and there's no annual cycle there either. So with this data, we can now build our statistical model, which I've called HOT-D. I'm not going to go into the details. There's a paper at the end which I reference, which has just been accepted using this for those who are interested, want to go into more detail. But this model really is only looking at this upper tail, so all data above this non-stationary 94th percentile. It's not very sensitive to that choice, but that's what I've chosen for this particular application. And the structure of the model is as follows. We begin an event, and then we seed that first day temperature, and then we propagate it through time, selecting from appropriate distribution of hot temperatures, where we use a conditional extremes model to capture this day-to-day dependence. And then we look to see if it ends with appropriate probability. And most of these will depend on time of year and climate change. Simulation is straightforward, requiring a particular level of climate change or a year to be specified, and either a day of year or a range of, like, the summer season. And so we spawn a lot of events, and for each of these events, we select a value for the first day from an appropriate extreme value distribution. This is then propagated forwards in time by sampling from a Heffernan and Thorne model, which ensures that the extremal dependence with time is preserved. And then we see if that event should be terminated, and if not, we continue propagating forwards in time. This is all very well, but does this HOT-D model produce a realistic series of daily temperatures? The problem being that the whole point is to try and produce events that are not seen in the observed data. So how do we do this validation? So to do that here, I've chosen to fit this HOT-D model to temperatures from a 100-year run of HADCM3 that has been forced with the SOS AT run. But then I simulate for a pre-industrial climate, that is a one-time CO2, and extract the heat waves from that. And then I compare empirically with a long control run, a 3,500-year pre-industrial control run. So they're independent, but it's quite a severe test because I'm trying to simulate a climatology that's not included in the original training data set. And just a few plots to show that it works quite well. Here are QQ plots, so observed, or this training data against the simulated data temperatures for day 1, day 5, or day 9 of a hot event, and those agree very well. And you can also compare the distributions of durations that both have on the left-hand side, and that seems to validate very well. And on the right-hand side, I'm plotting a comparison of the training data severity, and the severity here is an integral of the temperature anomalies over the duration of the event. So it's a metric that captures both magnitude and duration. And again, those seem to agree very well between the training data and the simulated data. Those are a bit esoteric. A slightly sort of more intuitive way of looking at it would be this annual cycle of temperatures. So the smooth lines here are the bottom is the 10th, the middle is the 50th, and the top is the 90th percentiles of all temperatures over this time-varying 94 percentile threshold. The grey events in the background are a subsample of 1,000 hot events from the training data. The thin black lines, both the red ones and the black ones, are samples of events with a particular severity from both the training data from the control run and the simulated data. spread out through the year, just so that you can see how it behaves through the year. And as you can see, they both agree very well. And you probably wanted to know, well, the black is the training data and the red is the simulated data. So with that confidence that the model seems to be recreating the climatology of the data that we put in, we can then see how we can use that for applications. So returning back to the Moscow 2010 heat wave, this points at the same data, the events again in the blue, although I've extended it slightly to a lower threshold, beginning and end dates. And what we can do is we can simulate two event sets, one for 1950 and one for 2010, and we can then determine how the likelihood of such events like the 2010 heat wave has changed. So this lower orangey peach band of numbers, that represents the 1950 20th to 80th percentile of all heat wave events that are over 10 days. And the purple is the equivalent, but for 2010. As you can see, the whole climatology has shifted to higher temperature values, thus showing that such an event like the 2010 heat wave has increased in likelihood by some large degree. On the right-hand side is a slightly different way of looking at things. These are now return level curves. For this bottom set is the present and the top set is the future, for different events of different duration. So the red is 2-day events down to the pink, which is 6-day events. And these are the return level curves that come from producing these large event sets that were created both for 2006 for London, and then the top set are for 2099 of this particular CMIP5 model forced with the RCP 8.5 scenario. And as you can see, there's a substantial increase in expected heat waves. And from these two curves, you can calculate the sort of relative likelihood changes by going left, right, or intensity changes by going vertically for your particular metric of choice, which duration you're particularly interested in. So just to sort of quickly
Simon, we can't hear you now. Simon, we've lost your sound and your slides. Okay.
How about that? Am I
Yeah,
back?
I can hear you now. Yeah, but we did lose your slides.
Sorry about that.
Just the last 40 seconds.
So should I just carry on with the conclusions?
Yes, please. Yeah.
Have you gone? Yep. So this can be used to look at the changes in distribution severity and very rare event probabilities. But the sort of slightly unusual thing is it actually provides actual event sets of daily heatwave events that can be used for impact studies, such as the thermal behavior or response of buildings or infrastructure. Here, the paper, as I mentioned earlier, on this using this work has just been accepted, and it can be seen at that particular site. And then we're also now thinking about future extensions of how to include humidity and diurnal cycle within the simulated events. And that is it.
Okay, thank you very much, Simon, and apologies for those of you who are having some technical problems with the audio. we're trying to provide suggestions in the chat, but I'm going to hand over now to Daniel Cotterill next, who will talk to us about extreme precipitation next. So Daniel, over to you.
Yep. Should be able to see now.
Yep, we can see that. Thank you.
Perfect. So I'm going to talk to you about flooding and changes in extreme precipitation over the UK. This project has been funded by the SPF UK Climate Resilience Programme, and most of the content I'm going to show you in this presentation is from a paper I recently submitted with co-authors Peter Stott, Nikos Christidis and Elizabeth Kendon, titled The Increase in the Frequency of Extreme Daily Precipitation in the United Kingdom in Autumn. So the motivation to look at both extreme rainfall totals and focus on autumn came from the South Yorkshire flooding event we saw in November 2019. Here we saw 1 fatality, 500 properties flooded and over 1,000 evacuated as 2 rivers burst their banks. This mainly came about through extremely high rainfall totals on the 7th of November, where over a month's rainfall fell in less than 24 hours in some parts. And on top of this, the river catchments were already saturated. There was a very high rainfall in September and October that year, and again some very high 24-hour rainfall totals just 2 weeks earlier on the 25th of October. And to give you some idea of those totals, I think if you take Sheffield, for example, it's around 64 millimetres on the 7th of November and around 47 on the 25th of October. Now, to give a bit of background, the intensity of extreme rainfall events are increasing globally with increases in global mean surface temperature, with the Clausius-Clapeyron relation the main mechanism behind this change. And basically, Clausius-Clapeyron relates saturation vapor pressure to temperature. And in basic terms, basically 6 to 7% more moisture can be held in the air as the surface temperature increases per unit Kelvin. So the aims of this initial work are as follows. Firstly, to quantify how the frequency of extreme totals are changing, have changed already in the observations. Secondly, to analyse using the latest high resolution UKCR 18 climate projections, how they're projected to change in the future, and particularly in the next 50 years or so. This would also take a focus on autumn, and in this case I'm using October to December. And lastly, this work won't actually be included in this presentation due to time limitations, but I also examined whether climate change had an influence on the November 2019 South Yorkshire flooding. So the index I'm using for extreme rainfall for the UK is R50 millimetres. And in summary, this is the number of daily precipitation totals that exceed 50 millimetres per year in October, November, December. Now I calculate this particular index for each grid box, and if I'm going to take a UK-wide or region-wide average, I basically take the mean over all grid boxes. And to give you some context to what 50 millimetres means for the UK in general, if you take any grid box, you'd expect perhaps it to occur around 0.1% of the time. You'd expect to get daily totals exceeding 50 millimetres. Now the regional climate projections are what I'm using for this work. I'm focusing mainly on the regional 12-kilometre ones. These contain those 12 ensembles of 100 years of data with no breaks from 1980 to 2080. I'm using a representative concentration pathway of 8.5. Now this is the highest emissions scenario, so to keep that in mind. And I also used the HAD UK gridded observations, which are produced in the Met Office Hadley Centre and are based off land surface observations. This has daily precipitation data from 1891 onwards, gridded at different resolutions. So what I'm going to do now is I'm just going to show you some key results I found. First, starting with the observations, what we've got here is a 10-year rolling mean of R50 millimetres for the UK. I've only used the rolling mean for visualisation purposes here, not for any of the calculations. But what you can see, using again, this is the HAD UK gridded observations at 1 kilometre. You can see a clear increase in extreme rainfall totals in October, November, December from around 1970. This trend is significant to 0.05 level. And when you compare both the start of the 20th and 21st centuries, you can see a 60% increase in R50 millimetres. Now looking a bit into the future, here I've looked at the UKCP 18 regional climate projections, and I've got a past time period centred on 1990 and a future time period focused on 2070. These are 20-year periods, and what I've done is I've compared the average R50 millimetre index for each over both time periods. So in basic, if it's blue, it's increasing in the future, and if it's red, the number of extreme events is decreasing. As you can see from the plot there, for pretty much the whole of the UK, the number of these events is increasing by around 100 or over 100%. With exceptions of perhaps parts of the East Coast. Now I'm going to look at a more sort of quantitative result. So what I've got here is I've got the UKCP 18 projections in blue. The shaded region represents the ensemble range. The blue dots represent the ensemble mean, and the black dots represent the observations for that year. Again, this is October, November, December. And what I've done here is I've compared the model and observational trends for data where we have both observations and model data. As you can see, the trends are pretty much identical for both, but the model slightly overpredicts the number of extreme days. So what I've done here is I've just applied a small shift correction based on return period, so that there's the correct number of extreme days. Now, what we've got here, this is the bias corrected model results. And what I did is I fitted a UK mean surface temperature to R50 millimetres, used the relationship between that to plot an exponential curve relating to show how R50 millimetres is projected to change over time. The best fit is an exponential fit. I've also plotted a linear fit here. This is the dotted line to show you the difference. But the key result here is that using this trend between 2020 and about 2080, we're going to see an 85% increase in the number of R50 millimetre events. This is just a projection. I'm going to quickly show you my key findings. The key findings are extreme daily precipitation events are projected to increase at an exponential rate in the UK. And there's an 85% increase likely between now and 2080. Extreme rainfall is projected to increase for all regions of the UK, and we've already seen this in the observations already. And very lastly, I'm just going to show you what some of the plans beyond this work we want to do. We plan to use river flow as a metric, and hopefully use a high resolution flood model in combination with UKCP 18 projections. So river flow data can be used for that, and it can be translated into impact metrics such as water levels, which are very useful. And the advantages of this takes into account the limitations of my current work. So our current work only really looks at extreme rainfall days, but river flow will take into account evapotranspiration, which is changing as UK surface temperature increases, and also will take into account the conditions previous to flooding events. So how much rainfall was there? For example, the Yorkshire flooding event, it will take into account the September-October rainfall totals as well as just the extreme events. And it will also give a regional breakdown with impact prediction more localized. And yeah, I want to thank you for listening, and that's it for me.